It's my great pleasure to welcome today my friend and colleague Omiros Papaspiliopoulos, who flash news. I don't know if anyone knew about it or is now at Bocconi University after a few other affiliation in Europe, in the UK, and in Spain. Omiros is a good friend of mine, as I said, has made many good papers, excellent papers on MCMC in particular, and or you can play with a model to reparameterize it to make MCMC work better, for instance, this kind of ideas, among many other things. Today, Omiros is going to talk about scalable computation for Bayesian hierarchical models. And these co-authors are Tim and Giacomo, whose name you can see on screen. They are also present. They will also help Omiros to answer some of your questions. So thank you, Omiros, for giving this talk today, and you have the floor.
All right, thank you very much. You should have said that we have the book and try to advertise the book, but anyway, let's...
I'm sure you will do it, so...
You should do it at every possible occasion. Anyway, so thanks for this invitation. Actually, that's a seminar series that I have personally attended times, and I like the idea and the topics. So I'm very pleased to give one of these talks. You couldn't have picked a better pair, me and Art Owen, back to back, because he's very likely that he's going to talk about something very related about this material. Here you will see that coming in the seminar. And as Nicolas said, actually I've just moved from Barcelona to Milan. Bocconi, I'm starting actually on Monday, but you know, sort of mentally I'm already there. So. Okay, so the talk is about scalable computation for Bayesian hierarchical models. I will tell you for what kind of models and what kind of computation. But the most important thing to start with is to tell you what means scalable. So scalable here, I'm thinking of the computational complexity of the algorithm to be at most its dependence on the two important parameters, the number of data points and the number of parameters in the model, to be linear or better than linear. So not worse than linear. I will explain exactly what computational complexity means, but think of the amount of work you have to do to get an answer. Okay. And I will be interested in, well, I will produce both methods, numerics and theory for scalability. And this is going to be a non-asymptotic theory. So in the sense that the arguments are not going to be based on some kind of large limits, but we're going to be interested to see how this non-asymptotic theory performs, especially in large limits. So in some sense, we're going to consider asymptotic regimes and try and see what this implies in terms of scalability. At the end of the day, scalability, it's a property in large dimensions. So, and I'm going to consider asymptotic regimes where both the number of data points and the number of parameters grows. Okay. In the talk, whenever I say that the computation can be done efficiently, and I will actually always highlight the word, with italics like here, I will mean basically that it can be done at a cost which is linear in the number of data points and parameters. Okay. As Nicolas said, there's going to be 3 parts in the talk, and in between the parts, I will take questions. So, and hopefully you can actually use your voice, which is way better than posting and collaborating, and we can have a more interactive session. Okay, so basically, I want to start by stating some facts with a question mark, whether these are facts or not. This is one of the things that the talk is going to debate, about scalable computation for large scale problems. So one is that the MCMC is really not appropriate for basically large scale applications. It's not scalable. And it's not competitive, computationally speaking, at least in terms of computing times. It's not competitive to variational methods. Another kind of, let's say, fact with a question mark again is that if you are going to use in high dimensional problems, you're going to use some MCMC, then Hamiltonian Monte Carlo and its variants are the main competitors. Another sort of widely believed statement is that if you have sparse dependent structures in hierarchical models, and there is some Gaussian priors, etc., sparse linear algebra should be helpful. Like you should be able to use it, and you should be expecting to get some good performance and potentially some scalability that explores the sparsity. I actually don't think any of these things is actually a fact. I call them these tales from the crypt. They are commonly held beliefs, but not substantiated. So part of this talk is not to be, in some sense, argumentative about the different methods, but actually to produce some theory that can substantiate these claims or prove them wrong when they shouldn't be believed. And it is to provide solid theory for useful algorithms, for practical algorithms. So the plan of the talk is going to be, as I said, split in three parts. The first one is an overview of the models I'm going to be interested in, the methods, the computational methods I will be considering, and to give you an overview of the results. So I will start by showing actual results on different problems. If you like, it will seem as if this is like the ballad of the Gibbs sampler. Like this is like, you know, the good old Gibbs sampler, how well it works in very complicated problems. That's not the idea. I'm not trying to sell the Gibbs sampler as your the method you use all the time. Although in these examples you will see that it works really well, but it's more like to be pragmatic and substantive about the claims. Then I'm going to I'm going to focus on one of the kind of models I'm going to be interested in, which is cross-effect models, and I'm going to describe the methodology we use for such models. And then I'm going to basically look at sparse linear algebra methods and see what theory and what results you should expect sparse linear methods to provide to you in hierarchical models. The material in this paper that we have been working for a number of years with Giacomo and then more recently with Tim is actually motivated by two real fairly large-scale applications, actually some consulting projects that Tim and I had worked some years ago. And in fact, the failure of commercial software to actually make inference for such problems. So it's actually really motivated by the unavailability of simple solutions for difficult practical problems. So that's actually the starting point. These two applications, I will sketch them right away so that basically, and then I will be using them to demonstrate the results throughout the talk. Okay. All right, so basically we're entering the first part of the seminar. And as I said, there are going to be models and there's going to be methods. And I think the models are basically the two workhorses of applied statistics. The one is nested multi-level hierarchical models. Basically gives you the canonical way to do hierarchical shrinkage in regression type models. And the second is cross-effect models, which is basically the modern version of ANOVA, analysis of variance, okay? So this is, in some sense, the two most canonical applied statistics Bayesian hierarchical models. And the methods that we're going to be considering in order to learn this and make inference and predictions with these models is going to be primarily Gibbs samplers, methods based around sparse linear algebra, which I will explain, of course, and belief propagation. I'm not going to talk almost at all about belief propagation in this seminar due to time constraints. So for these methods, we have theory, apart from new kind of implementations which they are scalable, but we also have theory of scalability, or we have theory of lack of scalability. In all the numerical examples I'm going to be showing you, I'm going to be comparing with things like mean field variational approximations as implemented in STAN, and also Hamiltonian Monte Carlo methods as implemented in STAN. And the results I'm going to be discussing here are going to be indirectly or implicitly relevant to Laplace approximations and the variance like INLA, for instance. So that's the panorama. So the main thing to do right away is to provide the two motivating applications, one for which nested models make sense and the other for which cross-effect models make sense. And these are the two applications I'm going to be showing you numerical results for later on. All right, so so the nested multi-level models is basically a canonical statistical structure to exploit data which they are given to you in some sort of nested structure. For instance, students within schools, within districts, within regions, etc. Actually, the application we are going to be presenting here, and it was one of the two large-scale consulting projects that Tim and I worked on, is basically doing some, well, it's part of a much bigger project. So here's a little part of that project, which is basically to model real estate prices at the postal code level in Spain. So what you see on the right-hand side is the map of Spain in little pieces. Each of these little regions you see there at the very high resolution is a postal code. There are 5-digit postal codes in Spain, so there's basically that defines a level of aggregation of the country. The full 5 digits describes a small region. The 4 digits is a slightly larger region within which you find a small region, etc., etc. So in this example, basically, there are 5 levels, as I said. And the data are organized as a tree. There's a tree structure going from the leaves, which is the 5-digit postal code, all the way to the root, which is basically a single code. The purpose of this analysis here was to understand how the local average square meter price in different types of properties relates to national variables as they evolve over time, for example, the GDP or similar type of indices for doing an analysis which is much more complex and involves many more data sources than what I described here. This is a little part of that business. So in this example, the data, and actually throughout my talk, the data is going to be denoted by bold Y, the vector of all available observations. In this application, this is about 4 million observations. There are actually also quarterly data for a number of years throughout the whole country for a number of properties. And basically at the leaf level, so basically at the postal code, at the 5-digit postal code level, you have a regression model, which regresses average square, log average square price per meter as observed in the market, and regresses that to some explanatory variables. So you have a regression at the leaf level, and then you take the coefficients of this regression and you start shrinking them hierarchically all the way down to the root. So the 5-digit level regression parameters are shrunk all together to a 4-digit, to a 3-digit, to a 2-digit, to 1. Okay. The prior in this model is basically conditional Gaussian. So the regression parameters throughout the tree are modeled by a very high dimensional Gaussian distribution. The total number of regression parameters in this model is about 8,000. Throughout the talk, regression parameters are going to be denoted by theta. And there's a number of precision matrices that they control these links in between the different levels of the hierarchy. And they generally will be denoted by gamma. This is a notation I'm going to be using throughout the seminar. Now, in practice, of course, you might have, in this particular application, we use data only at the leaf level, so basically at the 5-digit level. But in principle, you could have different types of covariance or even different types of output variables throughout the tree, all the way to the root, depending on the application. Okay? So an important concept throughout this seminar is that these hierarchical models will have certain sparsity. So in this example, I will explain to you what the sparsity is. It always means the same thing throughout my applications. It just takes different guises. The sparsity here is about 10 to the minus 4. What does the sparsity mean? It means in principle, there is the fraction of elements in the posterior precision matrix, which they are non-zero. Okay, so it's basically the fraction of relevant interactions between the parameters in the model. Okay, so there are thousands of parameters. There's only a small number of them. There are they are dependent in the posterior, and that's basically that fraction. Okay, so some says is the number of non-zeros in the precision matrix, if you like. All right. The likelihood function doesn't have to be, so in this model, the kind of models we're considering here, they have high dimensional Gaussian priors, not necessarily Gaussian likelihoods. Okay. So that's an example of nested models and an application. Here's an example of cross-effect models and another application. So basically, cross-effect models, if you like, is the canonical way to regress a variable on categorical covariance. Okay, so the example here is again part of a bigger project, but this part I'm describing here can be understood very simply. I have pre-electoral surveys for people who are sampled throughout the country in Spain again. For each of these person interviewed, a number of categorical covariates are recorded, in particular those that they are listed there on this table. So basically you see in which province of the country they live. There are 52 such provinces. What is their occupation, whether they work or not, what is the age group, what is their educational level, etc., etc. So there are in our analysis 7 categorical covariates. And there is a response variable, which is in this application is a multivariate response, is basically which of the possible parties available for the next election the person is planning to vote. Okay, so you have a multivariate response, it's like one hot encoding of a categorical variable, and you have various categorical predictors. So so basically the data form a contingency table, actually a very high dimensional contingency table. In this example, there are about 35,000 cells in this contingency table. There is, in this analysis here, there are about 10,000 respondents. So the survey consists of 10,000 people. And with a multi-logistic likelihood. So you have a non-Gaussian likelihood. And the model, which I'm going to describe to you in more detail further down the road, and I will give you a little instance of that in the next slide, basically takes again some kind of is an additive regression model, which the coefficients in these regression coefficients in this additive regression model, they're modeled by some conditional Gaussian prior again. This will become more clear as we go along. In this example, there are about 200 regression parameters and several known covariance matrices and precision matrices. The sparsity here is about 15%, and this 50% refers to the number of cells in the contingency table for which you have an observation. So in principle, this data, this contingency table that is the cross product of all the categorical covariates consists of 35,000 cells. Only a small fraction, 15% of those are actually contain some data in it. Okay, so right. So basically, this is, as I said, the modern analysis of variance situation, if you like. So here is a nice, simple version of this model, which is worth keeping in mind throughout my talk, and will make your life easier, especially when things get a little more complicated notation-wise. So the case of two categorical factors. So it's actually quite intuitive, and in fact, you can think of it as a recommender system. So, and actually, this is an interesting intuition for thinking of different asymptotic regimes. And let's put that into the perspective. So when you have only two categorical predictors, you could think conceptually, or it could be actually the application you're interested in, but it's useful to think of it like that in general, that the one categorical covariate is basically customers, and the other categorical covariate is a product, and an observation is a rating of product by a customer. So you have customer effects and you have product effects. And then the model, basically the structure of the model is that the rating depends in an additive way on the customer effect, let's call it A1, and on the product effect A2 plus some general mean, which is A0, okay? So this is basically the general structure of cross-effect models. You decompose the uncertainty, the variance in the observations in a contribution from each of the categorical factors, okay? So we will return to the interpretation, but it's a useful, simple cross-effect model to keep in mind throughout the talk. All right. Right. So basically, and I will return to this notation in more generality later on today. Okay. So basically, what is the computational framework I'm going to be considering? The aim throughout my seminar is going to be to obtain samples or approximate otherwise, maybe by some variational approximations, is to basically explore the distribution, the joint distribution of the regression parameters and the precision matrices conditional on the data. The methods we are considering and developing theory for, they do it always in the same scheme. They do a Gibbs sampling loop where you sample from the conditional distribution of the regression parameters given everything, and the conditional distribution of the precisions given everything. Now, the second step is sort of very low dimensional because there are a small number of these precision matrices and they're not very high dimensional because of the structure of the problem. So the big challenge is the first step, is how to efficiently sample the high dimensional regression parameters, okay? This is where all our methods will differ, okay? They all will follow the same structure, but they will differ in how you do the first step. And when I will talk about theory, the theory will refer to the first step, okay? So in some sense, it's quite unlikely that anyone can develop a useful theory for the pack of the two steps for a number of reasons. But it actually turns out to be at least tangible to get some interesting theory for interesting methods for the first step. And I'm going to be showing you an overview of such results, okay? So when I talk about scalability, I'm going to be talking about the scalability of the first step. And this, as you will see also in all the numerical studies I'm going to show you, it implies the scalability of the package because it is the first step, which is really the challenging one with a very high dimensional one. So the two methods, the two models I described, the crossed effect and the nested effect, they have things in common and they have things different. What do they have in common? I mean, in both cases, the priors on the regression parameters is going to be a high-dimensional sparse Gaussian distribution. Okay, this is how these models are typically set up. The likelihoods are going to be non-Gaussian, but the priors are going to be Gaussian. And what is another thing which is common is that sampling, the second step, sampling the precision matrices is going to be typically straightforward, low-dimensional sampling problem involving Wishart and gamma distributions, etc. Where the two methods differ radically is how the posterior dependence arises. So in nested multi-level models, the posterior dependence is actually driven by the prior. It is the tree structure that generates the dependence, and the data create, they do not change the dependence, they only change the sort of the diagonal of the precision matrix, not the off-diagonal elements. In cross-effect models, a priori everything is independent. It is the likelihood that creates the dependence. So a priori, the effects of a particular customer and a particular product are independent of each other. Once you observe that a specific customer has rated a specific product, they are linked together. So it's the likelihood that drives the dependence in cross-effect models. It is the prior that drives the dependence in nested multi-level models. And this will make a huge difference in what works for either. Okay, so let me start by showing some results, and I will spend the next 6 minutes or so or even 7 minutes or so on looking at these results. There's a number of things to explain to you here, and they basically give an overview of our methodology. In none of these results, our theory applies. They're all situations beyond our theory, but it's what our theory predicts. And what I want to show you here, it actually predicts interesting stuff. So in all of these examples I'm going to show you, we are fitting the full model with all the precision matrices, and I'm reporting performance of the algorithm that does everything. Okay. When that's not the case, I will explain explicitly. So let's see first what we see in this picture here. So this is the election model. So it's basically the cross-effect model for predicting elections with a multivariate output variables and a number of categorical predictors. So what you see with the orange color is results from mean field variational base as implemented in STAN. What you see with blue colors is our proposed Gibbs sampler, which I'm going to discuss later on today. So basically orange is variational base, blue is MCMC. The x-axis is real time, is world time. So basically it is the amount of time you need to run the algorithm to get some answers. The initialization and everything between the two things is comparable. So everything has been done quite carefully here. I don't have time to go into details, but take my word for it. So what we do here is that we look at all the regression parameters in the cross-effect model. And for each one of these regression parameters, we basically run very long MCMC chains for which we take the posterior mean and the posterior standard deviation as ground truth. And then basically we start, as you run the Gibbs sampler we propose and the variational base, after a certain amount of time the algorithm has been run, we see basically how far the estimate you get is from that ground truth. So you look at the absolute error of estimating a posterior mean and for estimating the posterior variance of a particular regression parameter. What you see on the top line is that you take all these thousands of regression parameters, or hundreds in this example actually, and you look at the median error. And we run every algorithm 10 times. So the number of dots you see per run is for different runs. So we actually rerun the algorithms a number of times, and we record what is the, among all the parameters, the median error, and we plot that. And on the bottom, we see the maximum error. So what's the worst error among all the parameters. And what's actually really striking here is that it's not that the MCMC, of course, will give eventually smaller approximation errors because it's meant to be giving unbiased answers in the end. But it actually does so much faster than variational inference in this example. So for the same amount of clock time, you actually get much better results. And that's actually shown by having the orange points lying way above than the blue points. Of course, the yellow points, the orange points will not necessarily convert to 0, but they will flatten out because there will be some approximation error, whereas the MCMC is not going to have such approximation error. But you see that for the same amount of time, variational inference is actually way worse. So it's not competitive computationally here. A note on the computations: our code is Python code, is not optimized in some sort of on some kind of low-level language. So that has not been factored in this comparison. So actually, a better implementation, of course, would just make this even more striking the difference. Okay, so here's basically Gibbs sampling versus variational inference for cross-effect models. Here is keep sampling. Sorry, here is sparse linear algebra methods. Forget about the Gibbs that says there is actually this implementation is really a sparse linear algebra implementation. So the sampling of the theta parameters, or the regression parameters, is using sparse linear algebra ideas. So this is deep sampling versus, sorry, sparse linear algebra versus HMC, in particular the NATS algorithm, as implemented in STAN. In this example, we're plotting on the left the ACFs of the 20 worst mixing regression parameters. Again, the algorithm updates everything. I'm just showing you some of these coefficients. So on the left, you see basically the 20 worst mixing components. And blue is again MCMC and mixes really fast here. Sorry, it's MCMC using the sparse linear algebra for sampling the thetas. The yellow is HMC and it's just implemented in STAN. And on the right-hand side, you have effective sample size per second. And again, you can see that here the sparse linear algebra implementation, it is remarkably efficient, okay, compared to HMC. What is really the issue here with HMC is not that the samples are not good quality, is that it's really slow. Okay, and you can see that on the left-hand side, because the x-axis again is not iterations, it's wall time. So basically, for that amount of wall time, this is basically how quickly your autocorrelations have decayed. So again, here, this is an example for which we can actually prove that sparse linear algebra is scalable, and that translates in these results beyond if you like, the scope of what our theory is applicable to. All right, so here's another figure. I'm going to return to this figure later on because actually there's a few things to say here, which is not easy to do it with this amount of detail in the seminar. Here's basically crossed effect models is a specific design which I will explain to you later. And let me tell you what is the message to keep at this point from this slide, and I will return to this slide later on. Forget about the three different lines on the top. So there's basically 3 lines on the top on every figure, and there's 1 line on the bottom. Consider the 3 lines as if there were 1. I will explain later what the 3 lines are. This is a log-log plot, and it plots computational complexity, and I will explain how this has been computed, versus the number of observations, the number of the data set. These are all sparse observation designs. The left is a very sparse observation design, and the 2 other are sparse, but not as sparse observation designs. So in all of these designs, what we do is basically we increase the number of data points, and actually also the number of parameters increases as you increase the number of data points. I will give you more details later on. What is important to note here is the slopes of these lines, which basically they show how the computational complexity scales with the size of the data set, N. And what you can see is that the bottom line, which is basically our proposed deep sampler, you have a linear increase in time. So basically the slope is equal to 1. So the computational complexity grows linearly or even sublinearly in the number of observations. What you see with the other lines is how sparse linear algebra methods perform in this case. So here I'm using sparse linear algebra methods to sample the high dimensional theta vector in the Gibbs loop. And what you can see is that in the very sparse regime, sparse linear algebra is actually scaling cubically in the size of the data set. Whereas in the other less sparse regimes, the dependency is quadratic in the number of data points. So they're not scalable. So for instance, here is a success story for sparse linear algebra. Here is a really big failure story for sparse linear algebra. And what is interesting is that actually we have theory that supports these findings. It's not just numerical experiments. Okay. And I will tell you a little bit more about this as we go along. So before I wrap up this part A, let me just show some inspirations for our work, because I think it's kind of important to link. There's a small number of references in this talk. There's a large number of references in our article, but there is some inspirations in this work which I list here. I am going to skip this slide now, but I will return to it time permitting later on. I just, of course, point your attention to the last one, which is Art Owen's work, with whom we have an interesting sort of interaction research-wise over the last couple of years on this theme, who's the next speaker in this seminar series. So I will try to return to this slide at the end of my talk to explain in what way I find these inspirations for what we try to do here. Okay, so this is basically the first part. We could spend 2 or 3 minutes if there is some questions that you would like to ask for what I've just presented.
So Omiros, actually, there's one question from Eric Ford. Eric, I'm going to open your mic. Just give me 1 minute. Right, Eric, you should be able to talk now.
Thanks. I was wondering which of your findings about the relative performance of these algorithms is specific to the observations being sparse, and if it's a statistical fraction, how sparse does it have to be before these advantages show up?
Yeah, I mean, so it's a good question, but it's a really long question to answer, so I will not answer. I will try to answer this a bit later. The theory we have, well, the theoretical results we have do not require certain sparsity. I mean, there are basically, as I said, non-asymptotic results. So then what happens to the bounds we get or to the results we get as you explore different sparsity regimes? It's different, and this will become a little more clear as I show you some results actually as we proceed in the second part. But let me tell you one important thing, that for example, the fact that the Gibbs sampler, whether the Gibbs sampler is scalable or not, it will depend on the sparsity structure. Okay, and actually the same thing happens with sparse linear algebra. Whether it is scalable or not will depend on the sparsity structure, not just on whether there is sparsity, but also how the sparsity works. So let me go a little further down the road my talk, and maybe you can jump in again and we can discuss this with more information. Okay?
Great, thanks.
Right. So I move on, and then there's another stop further down the road, so we can.
There was a question on ACF, but I took the liberty to say that the ACF is an autocorrelation function.
Yeah, I'm sorry. Yeah.
And yeah, okay, we're done.
Answer also many questions, Nikolai, if you want. I don't mind. So,
please go on.
Yeah, so basically the second part is I want to give you some more insights about the methodology for the cross effect models. Actually, I'm not going to spend too much more. Actually, I'm going to spend pretty much very little time on the rest of the talk on nested hierarchical models because I skipped the belief propagation part. I'll tell you one interesting connection about belief propagation and sparse linear algebra later on. But the majority of the rest of the seminar is cross effect models. That's where things are a little are quite more interesting and quite less obvious actually. So let's revisit cross-effect models. Here is a mathematical description of the model in great generality, which is basically the white sort of panel you see on my slide. But let's not lose the simplicity of the simpler case I gave you earlier. So what basically the main structure in a cross-effect model is that the data the covariates are categorical. And at every cell of the contingency table, basically the observation you see depends on a latent quantity which reflects the level of the categorical covariate that corresponds to that cell in the contingency table. Okay, so let me just quickly jump back to this description here. So as I said, J is an observation, and this, if you've never seen this multi-level notation, let me explain this quickly. So J here is an observation, and for the level for factor 1, I1 J means the level of the first factor that the jth observation corresponds. Would be, for example, the customer that actually has made the jth rating. And I2 of J then would be the product that the jth rating corresponds to. In the electoral example, J would be a respondent. I1 of J would be the index of the province. I2 of J would be the occupational status, employed or unemployed. I3 of J would be something else, etc., etc. Okay. So the cross-effect model explains the data by this additive structure. Okay. So here is the model explained in full generality with everything multivariate, etc., etc. But the last line, if you like, is the most important. And the linear predictor is a linear combination of effects, and you have one effect for every level of every factor. When the data are multivariate, like in the election example, because the response is a vector of choices, when the data are multivariate, then also the effects are multivariate, because you have an effect like the propensity score to vote for each one of the parties for each of the levels of each of the factors. That's why everything is like bold notation, because are vectors. But the details are not so critical. The structure is what is critical. All right, so basically, and there could be, of course, non-categorical predictors, which are denoted by xj in this slide there, and beta would be some additional regression coefficients. So very easily you can add also non-categorical covariates. But the main thing here is going to be the categorical part, because that's going to be high dimensional. Okay. So as I said, let's not lose sight of the simple case equal to 2 and one-dimensional observation, L equals 1 in our notation. Basically, in this case, what the cross-effect model does is says everything is independent, all the levels of all the factors are a priori independent, and all the levels of a single factor, they are all drawn from the same Gaussian distribution with a common precision parameter. So the precision parameter determines how relevant that factor is for explaining the data. If the precision is large, then means that all these coefficients are shrunk to 0, so that factor contributes little. If the precision is small, that means that there is a lot of variability in this factor, which means that this factor is actually relevant. Okay, so this is the analysis of variance interpretation of the cross-effect model. All right, with this notation at hand, the model basically on top of this Gaussian distributions on the levels of the coefficients, it involves Wishart and gamma distributions on all the hyperparameters, which are variance hyperparameters, okay? Or other priors. Actually, there's a number of other suggestions in the literature for these precision parameters. Okay, so basically, let me give you the intuition for the methodology we're going to propose here. So for the type of Gibbs sampler I'm going to describe. So what happens here is that you start with a model with everything is a priori independent. Why they become dependent? They become dependent whenever you observe a particular cell of the contingency table, because then all the levels that correspond to that cell have to collaborate with each other to explain data points. So in some sense, you get some kind of constraint that the sum of the categorical factors, they have to somehow be near the observation, okay? Whenever you get an observation. Whenever you don't get an observation, there's independence of everything because there's no information, okay? So now, what is actually the key observation here intuitively is that the strength of that constraint. So whenever you observe a cell in the contingency table, whenever you observe a particular person from Barcelona who is unemployed, who is man, who is this, who is that, and votes for something, whenever you see this combination in the data, this immediately creates a dependence across the parameters that correspond to the corresponding levels of the categorical factors. The important observation here, which you can make theoretically valid, is that the strength of that dependence that the observation imposes is sort of equivalent to having observed one of the factors. It's as if you knew the regression parameter corresponding to one of the factors. So that's how much each observation contributes to the information. Somehow it provides that amount of knowledge about the vector of these levels. So this actually generates the main idea of the methodology we propose for dealing with cross-effect models in a scalable way. And then actually we prove that it's scalable, as I will quickly showcase here, which is basically to use what we call a collapsed Gibbs sampler. So in some sense, since the amount of dependence that an observation introduces is as if you knew a categorical factor, then try to not update single categorical factors, but integrate one categorical factor so that you basically alleviate the dependence that this has created to the vector of categorical factors. And in the categorical factor we actually always integrate out is this average level, okay, is the intercept, if you like, in this model, okay? So the idea of the method we propose here is basically not to use the Gibbs sampler in the most basic way, which you go and you scan through your all regression parameters and you update one by one according to the conditional distributions, but rather you do that, but in a slight variation where you, whenever you visit a level of a factor, you update it jointly with this, whenever you update a factor, you update it jointly with the intercept, okay? So that's what I described in the first equation there, that the idea is to sample iteratively the pairs of the intercept and the categorical levels of a single factor, scanning through the factors. That's the collapse idea here. All right, now that algorithm can be implemented exactly and efficiently if you have Gaussian likelihoods, because everything turns out to be tractable, as you could imagine. When you have non-Gaussian likelihoods, you can actually do an interesting variation. I am going to skip, I have actually a slide on this. I'm going to skip the details of the construction. I might return to it depending on the time and the questions. I would be very keen to show you exactly how you do it when it's non-Gaussian. But for the purpose of the seminar, it's good enough to keep in mind that it's something you can actually do efficiently. Okay? So I'll skip the details for now because I want to make sure to reach the end of my seminar. But I might return to time permitting. What is very crucial to describe here is what is the resulting complexity of this algorithm, and try to see what happens with its scalability. So let's first carefully think, what does it mean, the cost of an MCMC algorithm? So the cost of an MCMC algorithm is really the product of two quantities. One is how much time it takes to do one iteration, and the other is how many iterations you need to mix, to convert. So specifically, you can define the cost as the cost per iteration times the relaxation time. The relaxation time, you can think of it intuitively as the number of iterations the Markov chain needs to get a sample from the target distribution, or to get a sample from a distribution which is epsilon away from the target distribution. Okay, is the effort you need, the number of iterations you need to get a good sample. Let's put it that way. So for the collapsible sampler, in the general case, the method that I skipped the details of, you can actually establish that the cost per iteration is of the order that's described there on the middle of the slide. The main thing to notice here is that this is a cost that grows linearly in n, because you can see that dependence on n is linear, and linearly in p, which is the number of regression parameters. Okay, so here the cost per iteration is good. It's basically linear in the number of data points, linear in the number of parameters. That's great. Now, what is extremely hard, and if you are not a specialist, you might not appreciate how hard it is, but it's really, really hard. It's one of the hardest things in this scientific field, is to obtain useful results about the relaxation times of Markov chains for interesting algorithms, not for toy algorithms or for toy problems. This is an incredibly difficult problem. So it's really hard usually to get any quantitative understanding of the second term of this cost. But for cross-effect models with Gaussian likelihoods, so okay, this is we have to make a small compromise here to get an interesting answer. I cannot provide answers for the general algorithm, but we can for the algorithm which has Gaussian likelihoods. So for that algorithm, there was a major breakthrough in understanding the complexity in a recent article that Giacomo, Gareth Roberts, and myself wrote a couple of years ago, and it appeared last year by Mcmc, where a number of useful theoretical results about the relaxation time of such algorithms for such models they're obtained. So in particular, building on these results, again, I'm emphasizing that this applies to Gaussian likelihoods. Building on these results, we, under certain assumption on the design, let's keep this for a second, and I can return to it. We can obtain the following result, the following proposition, that the cost of Gibbs is of order n times the minimum of two quantities. One quantity is n bar. So you can think of n bar as the average number of observations per factor, per level of factor. So in some sense, it basically gives you it's a metric of how populated the contingency table is, like how many observations per level of each factor you have. Okay, so this is the n bar. If you have very sparse data, or if you consider very sparse asymptotics, to consider what happens as the size of the problem gets larger, n bar will be order 1. So basically you will get very sparse contingency table, and the amount of data per level of factor, so the amount of voters who are men or women or this or that, is going to be basically in very large regimes is going to be order 1. So so that's the n bar. What is the d aux? So let me explain to you what d aux is in the next slide. So what is this d aux thing? Is basically the relaxation time of an auxiliary Markov chain, which is on the co-occurrence matrix. So basically, for every, so this is actually a result, by the way, I should be a little more explicit here. This is a result that works for two factors, okay? So think of the recommender system, okay? That's probably the easiest analogy here. So think of the recommender system. So for the recommender system, we have two factors. Think of the potentially large setting where basically you have a large number of customers, a large number of products. The concurrent matrix is basically the matrix which is 1 if product I has been rated by customer J and it's 0 otherwise. Okay, so every time you get basically a combination of the two factors, you basically put 1, otherwise you put 0. Okay, so what this T-aux is an auxiliary Markov chain. It's an auxiliary Gibbs sampler, which samples as a Gibbs sampler from the conditional distributions of the normalized co-occurrence metrics. Okay, so somehow another way to see it, an equivalent way to see it, is that it's random walk on the conditional independence graph in this of the posterior distribution in such models. Okay. So this is actually a bipartite graph because you cannot connect, you always connect a customer to a product, never a customer to a customer, and a product to a product. So if you run a random walk on this contingency table, the relaxation time of this random walk is this T-aux. So this result is in some sense quite remarkable because it shows that the Gibbs sampler is going to work well, both in very sparse situations and in less sparse situations. When the data are very sparse, so when you consider asymptotics, which are very sparse, n bar is going to be bounded because basically you have very small observations per level. So you have basically the number of each customer, the number of products that every customer is going to rate is going to be order 1 because there are like so many products. So in those very sparse regimes, this is going to work well because basically it's going to be n times something bounded. So it's going to be order n. But if you're in less sparse regimes, so the contingency table gets quite populated, then this auxiliary Markov chain, which samples the conditional independence graph, is actually mixing quite well because there's a lot of things to move around. You can move from a customer to a customer quite easily because there's a lot of combinations that can get you there. So then this T-aux becomes the relevant term, and that's actually the small one. So that's why Gibbs sampling here is such a good idea. It works well both in very sparse regimes, but also in less sparse regimes. And to some extent, this relates to the question I received earlier. That's why I wanted to postpone it here. Again, the theory applies to Gaussian likelihoods. It applies to no updating hyperparameters. Here is basically some numerics that they are going beyond that, and they actually are for algorithms that you would be interested to apply in practice and for non-Gaussian likelihoods, etc. So what I'm plotting here is for an algorithm which updates regression parameters and precision parameters in the Gibbs loop. And what I'm plotting here is the following thing. It's actually the electoral example, but a smaller version of it to make the point with 2 factors. Plus the intercept. And what you see with blue is the collapsed Gibbs sampler. And what you see with orange is the plain vanilla Gibbs sampler, is the Gibbs sampler you would find in a commercial software. We know that in these situations, we have proved that in these situations, the plain vanilla Gibbs sampler is not scalable, whereas the collapsed Gibbs sampler is scalable. And one can understand also the reason why it's scalable. All right, so basically, in this example, it's impossible to say anything about the relaxation time because basically, as I said, this is a Markov chain, it's a complicated Markov chain. There's no way you can actually hope to say anything useful about the relaxation time. So what we do instead is we try to estimate the complexity, if you like, by simulations. And what we do is we report here the integrated autocorrelation time. It's basically the sum of the ACF that I was showing earlier, okay? So all of these algorithms, the collapsed Gibbs sampler and the plain vanilla Gibbs sampler, they have cost per iteration, which is order n. So it's basically, that's a good thing. So the main thing that will determine the scalability is the relaxation time. So here, large values are bad. It means that there's a lot of autocorrelation. Small values are good, means that there's very fast decay of the correlation. The Markov chains are mixing fast. So what you see on the x-axis here is what happens as you increase the number of observations. And what you see with the blue, let's focus on the blue solid line for this discussion now. What you see with the blue solid line is that the performance, the mixing time, if you like, of the collapsed Gibbs sampler does not change. Actually, it even improves as you get more data. Whereas the performance of the collapsed Gibbs sampler, of the non-collapsed Gibbs sampler, of the plain vanilla Gibbs sampler, is actually getting worse with n. In fact, almost linearly. So in this example, the plain vanilla Gibbs sampler would have potential quadratic dependence on n, whereas the collapsed Gibbs sampler has scalable, it has linear dependence on n. What happens on the top equation and the bottom equation? So the top panel and the bottom panel. The top panel is for Gaussian likelihood, for which our theory is more applicable to, although the algorithm we apply here is not using the Gaussianity, is basically doing this alternative implementation, which I didn't talk about. So on the top, you have basically a situation with Gaussian likelihood. The bottom, you have a situation with binomial likelihood. So you can see that qualitatively, the 2 figures are looking the same. The main message here is that the driver of the results is the conditional independence graph, not the type of likelihood here. Okay, so that's the message to keep. These results are very robust to the type of likelihood. They're what drives the situation is the actual structure of the problem, not the details of the likelihood function, etc. All right. Again, there are some remarks on the theory which I'm happy to return to by taking some questions later about what is the underlying assumptions and how you can move beyond that. There's some very interesting recent work by actually Owen that I believe it could be useful to improve on some of the results. But we believe that the theory we have is that the strategy we follow is limited, but not the results. We believe the results, and we actually have numerical findings that they show the results are applicable way beyond. All right. So I promised the questions. I'm not going to. So because I'm not going to get to the third part, so I'm going to take them later. So let me at least sketch what happens with the sparse linear algebra. So the time is limited, so I'm not going to be able to go through all the things I wanted to tell you here. So the main thing to tell you is at least give you some of the results that we have, because at least I would like to highlight those results. Maybe during the questions, I can give more detail. So for the sparse linear algebra, we can actually study more carefully the dependence of the complexity on the important parameters, NNP. And we can actually say useful things both for nested models and for cross-effect models. We have some general results, but more or less these are available in the literature. But then the specific results are what is interesting here. So I'm focused on those for the remaining of my seminar. So the first thing is to say that we can prove that for nested multi-level models, the sparse linear algebra works, can be made to work. And in fact, it can be shown in some way to be equivalent to belief propagation. Okay, I clearly haven't told you about belief propagation, but those who know what I'm talking about, they can understand the connection better. So, so this is a success story for sparse linear algebra. Then the tree structure works like a charm for sparse linear algebra methods, and you can get scalability. And in fact, the results I showed in the beginning of the seminar were exactly in this situation. But the story with cross-effect models is very different. Okay, and it's very different for a number of reasons. I will only scratch the surface here. So here is some specific results. So with cross-effect models, you basically, and if you have sparse data, the precision matrix is going to be sparse. So you're going to be in the sparsity regime. Okay, so the number of non-zeros in the precision matrix is going to be basically order number of observations. Okay, not the square of the observations. So this is a situation where you would hope sparse linear algebra to be helpful. But here is a result. The first statement you see, there is a result about the computational complexity of sparse linear algebra methods for sampling theta given gamma and theta. It's basically lower bounded by this k cubed. K is the number of factors, and the number of observations. N bar is the same quantity as before. It's basically the average number of observations per level of factor, from which you can immediately obtain the following corollary, that if you have two factors for which our previous theory applies, the cost of Gibbs is better than the cost of SLA. So actually doing collapse Gibbs sampling, you get better performance than direct sampling with sparse linear algebra from the posterior distribution of the regression coefficients. Okay, so here's basically a result that shows an indirect method, the Gibbs sampler, has better complexity than optimized direct method using sparse linear algebra. And I'll finish with this picture that I started, that was the last one I gave in the part of the results, and I'll finish with that in my seminar. So let me explain a bit what happens here. So here is Gaussian likelihoods, and these results are obtained by numerical calculations, not by simulation studies. So we can actually explicitly calculate the cost of sparse linear algebra. That's what's plotted on the y-axis, is the complexity, is the computational cost. So we can explicitly compute the cost of sparse linear algebra methods, and we can explicitly compute the cost of the Gibbs sampler. We cannot give a formula for it because we're outside the regime where our theory applies, for which we have explicit formulae, but we can actually compute it numerically. Okay, so here basically there's no simulations; it's just exact results, exact computations, if you like. So on the y-axis you have the computational complexity of the methods. This is a log-log plot. Straight line means some kind of polynomial dependence on the size of the problem. Here's the size of the dataset n. And straight line means scalable, slope 1, and different slope means not scalable. So what I was basically, what you see on the left is a situation of 2 factors. The middle is also 2 factors. The right is with 5 factors. And there is basically a missing completely at random design. So basically the observations are in the continuous table are there or not there completely at random. Okay. On the left, you have a very sparse regime. So the average number of observations per factor level is order 1. So in this case, n bar is bounded and the Gibbs sampler is scalable because of this reason. So that's why you see the slope 1. In this regime, the very sparse regime, where you would hope that sparse linear algebra is very good, it's actually hopeless. It's actually cubic in the size of the dataset. The two other panels, the middle and the right, correspond to a less sparse regime, where the number of observations per factor level is actually growing with n, and in fact, it grows in a specific way. The middle is with 2 factors, the right-hand side with 5 factors. So in this case of less sparse observation regimes, the sparse linear algebra is better, but it's still quadratic. That's why the slope of these lines on the top are 2. In this case, the Gibbs sampler works well, not because of the n bar being small, but because of the auxiliary Markov chain mixing faster. And this is what comes to save you here. Okay. So that's the win-win situation of Gibbs sampling for these problems. I mean, generally speaking, and that's the last statement to finish off my seminar, is that the dependent structure that cross-effect designs generate, which are very unstructured, they're not banded, or they don't have some canonical organization, is such that it makes sparse linear algebra really inappropriate. And as a result, it makes Laplace approximation methods inappropriate, and anything which somehow tries to exploit Gaussianity and of the prior together with some sparsity. And that the situation is very different for nested models, for which I have theory that is scalable. Okay. I hope I gave you an overview. There are some things I skipped, but maybe with the questions we can revisit them. So thanks a lot for your attention.
Thanks a lot, Omiros. And actually, we have a question from Sarah. Sarah, I'm going to unmute you in a minute. Yes. Dawn, Sarah, you can speak.
Hi, Omiros.
Hello.
So I was just wondering, so in your cross-effects model, do you attempt to enforce identifiability, by which I mean of the parameters and the likelihood, by imposing a corner constraint or some to zero constraint on the fixed effects?
No, not necessarily. No. So the cross-effect models, the results we have, they're actually relevant both if you do some kind of identifiability constraints or not. I didn't mention anything here. These results here, we do get identifiability constraints. Just to be consistent with some other studies that have been, results have been published. But in fact, we have the methodology actually works even better if you don't do that. So that's not critical at all in these.
Okay,
sorry, when you say the sum of zero constraints, you talk about the multivariate cross effect, or for which exactly thing you refer to?
So I was just talking about, so that you can't add something to the intercept and then take something off all of the fixed effects. So to prevent that kind of arbitrary transformation.
Yes, you're right. So here, basically, we do not impose an identifiability constraint. But I think, Giacomo, you can correct me if I'm wrong, but we know for a fact, at least for the Gaussian case, that doing so, adding the identifiability constraint, is not giving you scalability. Is that right, Giacomo? I remember correctly?
Yes, so we did some theory for the Gaussian case where we impose identifiability, and the theory we have is that imposing identifiability always improves mixing for these models, so it helps, but not enough to get linear, to get order 1 mixing. And it depends on which identifiability you put, like fixing one factor to 0 doesn't help much. Fixing the mean helps more. But still, it doesn't remove correlation enough to get order 1. And in the non-Gaussian case, it's a bit harder to implement because then you don't have conditional independence, which we heavily exploit here for the non-Gaussian case. So definitely, in my opinion, not having identifiability here creates additional mixing issues, but is not enough to get scalability imposing that, although it helps.
Okay, thank you very much.
Yeah, just to add to this is that there is a number of things that between the Biometrica paper that appeared last year and this work, which is going to appear in arXiv very soon, There's a number of things we've tried that there are common practices, like parameter expansion, et cetera, like identifiability constraints, all sorts of these things. And both our theory and our numerics suggest that all of those are making minor improvements, but they never change the scalability of an algorithm. So the really fundamental thing, for instance, for cross-effect model is the collapsing, and all the others are really secondary.
Okay,
that was a very good question. Thanks a lot. Anything else?
I don't see any other question. I was wondering myself, could you say a few words about this alternate method you mentioned at some point? You said, oh, we have a Gaussian likelihood, and yet we still do something else that Gibbs step.
Yeah. So, I mean, the whole point here is that when you want to implement this collapsing, at the end of the day, you have to basically integrate out this intercept there. Okay.
Yes.
Now, this integrating out is analytically feasible with Gaussian likelihoods, because the whole thing is Gaussian and everything is kind of available, and it can be done efficiently. With non-Gaussian likelihoods, this is unavailable. So what we do instead is we don't really implement this collapsing because it's not realistic anymore. But what we do instead is what I described here, which is you do somehow a local reparameterization. So you move to centering the effects, which, by the way, if you think about it, makes a lot of sense, because in a way what you have here is that you have that the data are creating dependence because you have a non-centered representation, because you have a summation of independent things, and then you get an observation which kind of constrains them. So what is the sensible thing to do is to somehow center, which should work way better, and it does, yeah? And then update on the center parameterization version. So that's the idea we exploit. So in some sense, you don't do an exact collapsing, but rather you do this, you change the variables, and then you update the changed variables and you change it back, just to put it very briefly. So what is interesting here is that the numerics I'm showing you, for example, here, they do not do exact collapsing, but they somehow do something which is good enough. And you still get the effects. And this is what I'm trying to say, that, you know, the theory suggests good practices, and when you put these good practices for real problems, they work well. So in some sense, that's why I think the theory is useful here.
Just another quick question. When you mentioned variational base, you meant mean field, right? The standard variational. Yeah. Okay. All right. I don't see any other question. David, maybe do you wanted to say something or no? Otherwise, well, thanks a lot for thanks a lot, Omiros, and thanks to your co-authors for showing up as well. That was very interesting. So I remind everyone that we have another talk in 2 weeks by Art Owen, and another one 2 weeks after that. So stay tuned. Oh, there is maybe a question from John. John, just give me a minute and I will let you speak. Yeah, John, you can talk.
Hello, I was just hoping you could flip back to that local parameterization slide for a minute.
Yeah, of course.
Yeah, there's just a lot going on here.
Sorry, can you see it?
Yeah, I can see it. There's just a lot of words, and I didn't read it last time. Thank you.
Yeah, well, I mean, it would have been impossible to have read it. So it was too fast. So yeah, so basically, as you can see here, you basically give up on the exact marginalization, and what you do is basically a Gibbs sampling step, but you don't update the intercept given the factor. That would be plain Gibbs sampling, which doesn't work. You update the intercept given this centered variable, and then you update these centered variables that are conditionally independent. So this actually is a simple thing, but it's really good. It's very clever. It was Tim's idea, by the way.
And the adaptation, you do it at every step?
So the adaptation is basically, yeah, it's for, I think, for a number of steps, and then we stop. Tim can tell you, I don't know, can be more detail on that. But anyway, I mean, there is a number of scaling parameters, and all of them are tuned automatically. So.
All right, so let's see if there's any other question in the audience. No, I think we are good. So thanks again to Omiros and his co-authors. Let me clap on behalf of everyone. And let's meet in 2 weeks' time.
All right, thank you very much.
Guys, do you want to talk 2 minutes with the organizer, and then Omiros, we can talk again separately if you want?
Yeah, sure.
Okay. So David is going to send you a link for a quick gathering. Thank you, everyone. Goodbye.
Thank you.